Well, till now we had been studying the microstates, number of the states in the phase space, which were defined as the number of the states either defined in terms of number of particles, volume and energy in the case of microcanonical ensemble, or the number of the molecules, the volume and the temperature in the case of canonical ensemble. But sometimes it is often necessary to have a concept like density of states, which define the number of the states in a per unit volume. That's why it's called number of states per unit volume is defined as the density, and per unit energy range. Let's say we have an energy range between epsilon and epsilon plus d epsilon, then what would be the number of the states per unit volume per unit energy range? That is what becomes necessary, particularly in the field of condensed matter physics. We would now like to do some calculation of the number of the density of states for three cases. Particularly, one is a free particle, classical free particle, the second one is the relativistic particle, and third one is the ultra relativistic particle. So let us try to see how one can arrive at the density of states. Density of states, or in general it is called DOS. Okay. Now what we till now know is the number of states in phase space, how it is defined. Now we know that this is nothing but equal to d omega by h. Let's say if it is a or h to the power f if there are f degrees of freedom. So for number of states in phase space for f degrees of freedom, okay, where d omega is the elementary volume in the phase space, so 3f q and d3f p. Q is the generalized coordinate and p is the generalized momenta. So this is the number of the state in phase space for f degrees of freedom, with elementary volume of the phase space is given by this. We can even write this as equal to d3f q d3f p divided by twice by h cross whole to the power f. Okay. Now if we want to define the density of the states, which is defined as the number of the states per unit volume per unit energy range, then we can always define the density of states as number of states per unit volume per unit energy range. Okay. So for that we can define a quantity which can be called as G epsilon D epsilon, which is equal to the number of the states per unit volume per unit energy range. So we have to then define this as if you want to integrate it over a volume V, then this should be equal to per unit volume. So we have to multiply this with again the volume V, and this should be equal to the number. So we can write this as integration over d cube f cube d cube f p divided by twice by h cross to the power f. So this is going to give us volume into d cube f p divided by twice by h cross whole to the power f. Now if the space is uniform, phase space is uniform for p, then we can always write this to be equal to 4 by p
p square, there is a v dp. If it is a spherically uniform symmetric one, then we can always write d cube d3fp to be equal to 4 pi p squared dp, as we did in our thermodynamics classes in our UG sections. You can always make the velocity uniform and make in the Maxwell distribution, you can write that. In the same fashion, we can write 4 pi p square dp. So this is going to give us, so the density of states G epsilon, this is basically the density of states. Okay. G epsilon can be written as 1 by 2 pi h cross to the power f and 4 pi p square dp by d epsilon. So if we want to have an idea about the density of the states G epsilon, then we need to have an idea about the momentum energy relationship, which is called the dispersion relation. So you need to know what is the exact relation between the energy and momentum, then that is called the, so need to know the P epsilon relation, also called dispersion relation. This is something which is always important, even if we define or we want to derive or kind of mathematical derivation of Schrodinger equation, there also we want to write the dispersion relation. So what is the relation between the momentum and the energy? We have three particular cases, let's say cases and dispersion relation, momentum energy relation, dispersion relation. We would consider them individually. So if it is a free particle, classical free particle, then the energy is equal to p square by 2m. If it is a relativistic particle, then it would be equal to root over of p square c square plus m square c4. And if it is an ultra relativistic, then we have epsilon to be equal to pc. Then for example, for the particles like photons, we have the rest mass to be 0 and the particle move with the speed c, then that in that case, so these are the dispersion relation. And if we want to get dp d epsilon for all these three cases, if we want to find the relation between dp d epsilon, so for free particle, what is dispersion relation? Now that would be dp d epsilon would be equal to, so this gives for the first case p is equal to root over twice m epsilon, so that gives you dp d epsilon to be equal to root over of 2m epsilon to the power half, so half, and epsilon to the power minus half. Okay, so dp d epsilon is root over of m by 2, okay, epsilon to the power minus half, square root of, okay, make it. How about the second one? Here you can write p to be equal to root over of, so epsilon square minus m square c4 whole divided by c square square root. So that is going to give us dp d epsilon to be equal to, okay, make it p square c square plus m square c4. Okay, so dp d epsilon to be equal to we can write this. So dpt epsilon would be equal to 1 by c and a half to the power minus half. So epsilon square minus m square c4 to the power half, and then multiplied by twice epsilon differentiation. So that gives us epsilon by c epsilon square minus m square c4 to the power half. And how about the third case where p is equal to epsilon by c? Then that gives, this is the most simplest one, d epsilon to be equal to 1 by c. So this would be simply 1 by c. Now let us try to define the corresponding density of states. So for a particle, classical particle, single particle, the degrees of freedom are 3. So we can write g epsilon to be equal to, for degree of freedom to be equal to 3. 1 by twice by h cross cube, okay, and 4 pi and p square for free particle we can write 4 pi into p square is twice m epsilon, and dpt epsilon is m by 2 to the power half and epsilon to the power minus half. Okay, so this is going to give us 2 to the power half. So density of states, we can write this as 1 by 8 pi cube h cross cube into 4 pi, and if I write it as 2 and this is 4, then this would be 2m to the power 3 by 2 epsilon to the power half and by 2. So this is going to give us 1 by 4 pi square, because this twice m to the power 3 by 2 epsilon half by h cross cube. So this is the density of states for a free particle in 3 dimension. If we talk about the relativistic particle, then we can do that 1 by 4 pi square twice m to the power 3 by 2 h cross cube epsilon to the power half. So we have for this, again if I draw another column, then I can draw another column over here, and I can write the corresponding density of states, DOS. Okay, I can do that. Okay, let me write this. This is free particle, relativistic particle, and ultra relativistic particle. So this is relativistic particle, this is free particle. So for this, the density of states DOS, which is G epsilon, is given by 1 by 4 pi square twice m to the power 3 by 2 by h cross cube epsilon half. So we can say the density of states versus energy is something like parabolic. Now if we want to calculate the same thing for the relativistic particle, for which dp d epsilon, or we want to calculate dp d epsilon for the relativistic particle, this is the p dispersion relation. So we can write dp d epsilon. So this is p is equal to, okay, this was p is equal to, this is again p is equal to, so we can dp d epsilon would be something like dp, this is nothing but sorry, this is dp, so p is equal to e by c, and so dp d epsilon. Okay, so if we put this for relativistic particle, we can write this as equal to g epsilon is equal to again 1 4 pi, so 4 pi by 8 pi cube is always 1 by twice pi square, 1 by twice pi square, and h cross cube, and then p square dp. Okay, so p square is nothing but equal to this is p square is equal to e square, okay, e square minus m square c4 divided by c square. Okay, p square 4 pi p square, and dp d epsilon is epsilon by c root over of epsilon square minus m square c4 to the power half. So this and this cancels out, and there is, so this would be equal to 1 by twice pi square h cross c whole cube. Okay, there is an epsilon over here into epsilon square minus m square c4 whole to the power half. So what we have as the is 1 by twice pi square h cross c cube. So this is the relativistic particle, so we can say this is the expression. So this is 1 by this is 1 by twice pi square h cross c whole cube, okay, epsilon into epsilon square minus m square c4 whole to the power half. So that is the density of states for a relativistic particle. For ultra relativistic particle, we can again calculate the g epsilon for ultra relativistic particle using the same expression. We can do that. So this would be equal to again 1 by twice pi square h cross cube, and then p square, so that would be equal to epsilon square by c square, and dp d epsilon is 1 by c, so this is going to give us epsilon square by twice pi square h cross c whole cube. So this is going to give us the expression for the relativistic, ultra relativistic particle, which is 1 by twice pi square and epsilon square by h cross c whole cube. So we can calculate the density of state in such a fashion. We can even go for lower dimensions which had become recently very important in research. You can calculate the density of states for 2-dimensional system, for 1-dimensional system, and so on. Thank you.